Uh, in past lectures, we have covered the basics of strength of materials, which are the concepts like stress, strain, elasticity, the moduli, and then various kinds of loadings in beams and in pressure vessels. And also, we have seen how to transform the stresses from one coordinate system to another coordinate system. Now we will see one kind of loading which is a very special kind of loading, and it is also a very important loading because it is seen a lot in nature. This is known as buckling. Now, buckling is essentially it is basically a sort of instability in structure. Now, what buckling is, I take example of a column to explain what buckling is. A column is a structure which is designed to carry compression. It is designed to carry compressive load. So let's say that there is a long bar of length L, and let's say the width is P and the thickness is T. Some thickness is there, so area of cross section is BT. Now in this case, this P, if we ask what is the stress in the column, so the answer is quite obvious that the stress is P upon BT. That is a compressive stress. But this is not the only stress which gets generated in the structure. Besides this compressive stress, what happens is that the column also bends. It bends because P is not exactly along the center line of the column all throughout the length of the column. The reason for that is the structure, nothing can be built which is symmetric and which has exactly one line which is vertical, which is at the center along which the load always acts. It's not possible to have all these conditions happening. It's impossible in nature. So because of that, this column also bends. So if I just draw the column like this with a line and I apply this force P here, the column bends like that. This bending is known as buckling. This is buckling. This is a sort of instability because once it starts bending, it bends much more like this. It just bends completely like that. It collapses. So this loading is very important to study for structures which are simply supported, which means that if I have a column which is supported like this, and if I apply a P force, actually this will be these will be the this is the roller and this is the pin, and apply a P force here, and if this length is L and the material length modulus is E and the area moment of inertia is I, then the critical force P critical is an entity which is given by pi square EI upon L square for this case if P exceeds P critical, then buckling ensues, which means buckling happens. Now it is very easy to see that P critical is directly proportional to I and E, which means with higher value of cross section dimensions and with a higher value of E, buckling can be prevented or buckling load can be increased. But P critical is inversely proportional to L. it is inversely proportional to L square, which means that if the length increases, the critical load decreases, which means it's easy to buckle long structures or very high structures. So this is the kind of instability which sets in because of the inherent asymmetry in the structure and inherent asymmetry in the loading pattern. And this is a very important thing to read, because if we see now, if let's say that I take the same example which is taken here. So if I have the same beam which is having the cross section area as BT, for that I will be equal to 1 upon 12 BT cube, for example. So the P critical value will be equal to pi square EI upon L square, which is nothing but pi square E into 1 upon 12 BT cube upon L square. Now if I take a sigma critical stress, which is I define by this, that value is pi square EI, pi square E into, this is T square because BT is cancelled out, upon 12 L square. Now if we compare this with the value of the critical stress there, sorry, the compressive stress there, so sigma is P upon BT, that's the value of sigma. So if for example, if we have to compare the two values and say that equal force is, I mean the force which is applied here is taken as the critical force itself, and we will see that for this, if I just substitute the value of P critical here, or rather I say that this stress is equal to this stress, then I will see that a very small force P is able to create a very large buckling stress. This is the buckling stress, while the value of the compressive stress is very small. So what happens is, for a small value of P, the buckling stress is very high, and the reason for that it is inversely proportional to L square and directly proportional to T square. Now T is a very small number and square is much more small, or rather much less in number, while L is a very large number and its square is very much higher number. So overall the same force creates a very small compressive stress, but it creates a very large buckling stress. And large columns are, or very long columns, very high columns are prone to buckling rather than getting rather than failing under compressive stress. Now let's see a few examples. So if now please remember that the formula which has been arrived at is for this simply supported configuration, which is like this. This is simply supported configuration and the length is L. Now suppose I have the same problem, but it is like this. Suppose I have a large column like this and it is loaded with the structure P, and this is fixed here to the ground. Now for this, what happens is that this load will cause it to bend like that. Now you see, in this case what happens is, we can assume that this is, the whole column is like this, and if this length is L, so one end free and one end fixed can actually be simulated using a column which is of length 2L and acting as a simply supported column. So for this configuration, P critical is equal to pi square EI upon, I'll say L effective square, which is nothing but pi square EI upon, now this value is 2 times L, so it becomes pi square upon 4 EI upon L square. this quantity is equal to the buckling load for this one. So you see the buckling load for a beam which is fixed at one end and free at another end is 1/4 of the buckling load for a simply supported beam, and the reason is the effective length is twice in this case. So this is actually the most common structure which buckles, because this is a structure which is heavily found in civil engineering where buckling is a critical problem. Now let's see a few more questions. Now let's see the second question. So I take a very simple case of one bar. Now I take a bar which is like this. It is fixed between, it is a simple bar. Let's say the length is L and the material Young's modulus is E, and it is fixed between two rigid fixities. Now obviously I know that because these two ends are fixed, the length increase is not possible. Now I pose the question, what is the delta T required such that if that delta T, that increase in temperature is applied, the bar will buckle, assuming that the P critical is the critical load for this bar. Now we can assume that the bar has a square cross section of dimension T something. So which means that the cross section is like this. This is T and this is also T. Both these dimensions are T. So in this case I is equal to 1 upon 12 T to power 4. Okay. Now if I am given this condition and I am asked what is the raise in temperature required such that this bar buckles, so we have to now see that this bar is a fixed bar. In a fixed bar, the effective length is half of the original length of the bar. So please remember that in case of fixed condition, this is the thing, because in fixed condition the ends are not supposed to rotate. So this, when it buckles like this, because of which the length is actually effectively from here till here only, which is like a simply supported thing. So effective length is half of the total length of the bar. Now for this case we know that the P critical is pi square EI upon L effective square, which is nothing but pi square E into T to power 4 upon 12 into L effective is L by 2 square. So now this, if I solve this problem, I get pi square E T to power 4 upon, this becomes L square by 4 and this is 12, so this is 3 L square. So this is the critical force for this bar. Now what is the delta T which is required to create this kind of force? Now we go to the theory of thermal expansion. So there we know that the strain, thermal strain, is equal to alpha into delta T, assuming alpha is the coefficient of thermal expansion for this bar. So the stress caused by this, if it is not allowed to expand, will be E into alpha delta T. So the force will be E into alpha delta T into T square, because this is the cross section dimension or the cross section area. So this should be equal to this much force. So E alpha delta T T square is equal to pi square E T to power 4 upon 3 L square. So delta T is equal to we can cancel out T square from this side, and E gets also cancelled out. Delta T is pi square T square divided by 3 alpha L square. That is the amount of temperature increase which we need to apply to this bar such that it buckles. Now please see that this delta T is independent of the material, and that's logical also, because material constant will get will be like whatever happens to the thermal side will also be happening on the buckling side, and E is like a linear quantity in both of them. So for any material which is isotropic, this is the amount of temperature difference which is required to buckle the structure. It's a very good problem because it clears a lot of concepts. Now let us see a few more examples. I just change the page. So I take another example. So I take the example of a cylindrical pressure vessel. Now this time I have a cylindrical pressure vessel which has a fluid at pressure P. Its Young's modulus is E, thickness is T, and radius is R. This is what we had seen yesterday. Now for this case we know that the hoop stress is P R upon T. Hoop stress is like this. This is sigma hoop, and the longitudinal stress is PR upon 2T. This is the longitudinal stress, sigma L. Now I take this problem, and in this problem I make a modification. The modification is, if a force P is applied longitudinally to buckle this pressure vessel, what is the value of P? If a force, let's say F, because P will get confused with F is what? What is the value of F? Now you have to think a lot before solving this problem. Why? Because see, what happens is there is a sigma L which is a tensile stress in this case. Okay, now let us see what is the critical stress for or rather what is the critical buckling load for this. Assume that it is a simply supported structure and this length is L. Let us assume those conditions. So the critical load will be equal to P pi square EI upon L square. Now what is the value of pi square E upon L square? That's a constant. And I, the I value for this structure is pi r cube T. This is the value of the I for this thin tube. So this is the P critical, the critical buckling load, which is nothing but, if I just make it more compact, it is like this. This is the critical buckling load. Now please see, this is the compressive load which is required to be there in the structure. Right now there is a tensile stress which is there. So what is the tensile right now? What is the tensile stress? That sigma L is equal to PR upon 2T. This is the current tensile stress in the longitudinal direction. So what is the PL is A into sigma L. A is 2 pi r T into sigma L. So that is equal to 2 pi r into PR by 2T. This gets cancelled out. So that becomes pi P into pi r square. That is the, obviously that is the um, that is a load on the structure, or that is a longitudinal force which is acting on the pressure vessel right now. That is a tensile pressure, tensile force. So what we have to do is that the value of force which needs to be applied in this direction, like that, this is the F, should be equal to P critical, because that's the force required to buckle the structure. F is equal to P critical, which is the force required to buckle, plus PL, because that is the force required to overcome the tensile loading which is there. So both of them have to be, so first you have to overcome the tensile stress because of the pressure, and then you have to add additional P critical to buckle the structure. So the whole force, the total force will be equal to pi cube E R cube T upon L square plus P into pi r square. That is the total force which needs to be applied. Obviously, you may ask what is the use of this equation. This equation is useful because many a times what happens is that there are a lot of structures which are having internal pressure and they are under buckling load. One such example is our small test tubes, which may be under this kind of loading, and in those conditions, in those examples, this is the analysis which is required. Now let's invert this problem. Let's say that I just invert this problem into a very interesting kind of problem. Let's say I have the same kind of thing, but the pressure is minus P, which means that there is a negative pressure acting in the pressure vessel, and rest of the things are all same, E, R, T, everything is same. Now I ask a question, what is the negative pressure required to buckle the structure? Negative pressure means everything from outside will be coming like that. The pressure will be acting like this instead of outside. So in this case, it becomes again a very interesting case. Now in this case, what happens is that sigma L is minus PR upon 2T, because now it's a negative pressure, which means there is a suction happening. Now when this sigma L multiplied by area of cross section which is being resisted is nothing but minus P into pi r square is equal to P critical, which is already found out from this equation, then buckling happens. So I will say minus P, or rather in terms of numeric quantities, P into pi r square is equal to pi cube E r cube T upon L square. So that leads me to get value of P, which is pi square E R T upon L square. That is the amount of pressure which has to be there in form of a suction pressure in the pressure vessel such that it buckles. Now this is like a what should I say, this is a combined concept problem, which is there are 3 or 4 different concepts which have come into play in this problem. Obviously there is a concept of stress, and then there is a problem of pressure vessel, and then there is a problem of this buckling load and the criteria for buckling, etc., which have come into play in this problem. So this is a very good problem where we can figure out a lot of concepts and see how they interplay to arrive at certain quantity which is of practical importance for us. So in this way we have to solve buckling problems, and I request every one of you to solve many buckling problems and see how buckling loads, etc., generate the buckling stress, and how the structure, dimensions, and its geometry and constraint change the buckling load, because buckling is a very important phenomenon, and it's a very tricky thing to understand also, and because it's a kind of instability, so it hits without giving notice, sort of thing. So it simply comes from somewhere, and then it hits directly, and it's like an instability, so it suddenly hits, and before we have time to understand, we have got hit and the structure has collapsed. So understanding of buckling in complex structures is very important thing, and for complex structures there are softwares which check the, or which calculate the buckling load or buckling stress for us. So in case of such complex structures, these softwares need to be used, but for simple structures like beams and all that, this is a this analysis is sufficient. Now let's solve one last problem in buckling before we finish the chapter. Now I have a problem which is like this. It's a structure which is fixed at one end, and has another end as free end, and the length is L. And at this point, at the free end, I have a dynamic load coming, P dynamic. Now, what is the meaning of P dynamic? P dynamic normally is the force which is suddenly applied. So P dynamic is usually some n times P static, or the P load which is which acts very slowly. So if this is the condition, then what is the buckling? What is the condition for buckling for this case? It is pi square EI upon L square, but this in this case L effective is 2L, so it is 4L square. Now P, when P dynamic exceeds P critical, buckling happens, ensues. So that means N into P, when it is greater than pi square EI upon 4L square, then buckling will happen. This is P. So what that means is that P should be greater than or equal to pi square EI upon 4L square into N, where N is dependent on the speed of loading, and from the height it has dropped or something like that. But that's not the important thing. The important thing is that if we do not want the structure to buckle, then what we have to do is we have to make sure that P is less than or equal to pi square EI upon 4L square N, such that buckling is avoided. So if this is the case, then L must be less than or equal to pi square EI upon 4, or rather L square N P. So L is less than or equal to pi by 2 square root of N square root of EI upon P. Now you see, in this case only N is the number which is like a variable quantity here. Assuming everything else is a constant, N can change because you can drop the load from a height, or you can apply it very fastly and all. So the L is proportional to 1 upon square root of N, which means that if you are having the multiplication factor of very large number, its square root is the time by which you have to divide a length, which means the length has to decrease by the square root of that that multiplication factor such that buckling doesn't happen in the structure. So this is a very important problem in design of many mechanical structures, like for example the connecting rod of an engine, which is always under which is I mean half of the time under compressive stress, and it has to be designed with such a consideration because there the loading is very dynamic, and the length has to be such that the dynamic load is borne properly, because dynamic load is much more, or rather much higher than the same static force. So with this we end the chapter on buckling, and later on we will see a lot of problems in which have come in gate.